Hi, my name is Claudia Fotiu, and this is my Cap 1 for ATP pathways for Kin 516 Advanced Exercise Physiology. The objectives of this presentation are going to include the key steps involving the body's pathways of producing ATP. The molecules that we'll use are going to be glucose and then one molecule of fat, and we'll discuss their various pathways when we're utilizing those substrates. We'll additionally discuss the total ATP yield from each pathway, followed by pathway interactions across varied exercise intensity and/or durations. And lastly, we'll discuss factors limiting ATP production within each pathway discussed. So here we go, where this discussion is going to be with regards to adenosine triphosphate, abbreviated as ATP. So we've got on the image on the left, we've got our food, or our substrates, we can say, I guess, your macronutrients here. And we're going to talk about how the conversion into ATP for usable energy for work. So with this is kind of my illustration that I created here. It's going to be the adenosine triphosphate molecule. As you can see here, the square on the right, that is going to be your adenosine. So that's going to include your adenine, and then it's going to be bound to your ribose. Okay, and then separate here with the little blue image here in blue, these are going to be your phosphate groups, and you're going to have 3 phosphates. Okay. So this is going to be ATP production from a single molecule of glucose. So it's glycolysis here. We're going to start up at the top. I hope my cursor is visible. At the top you can see glucose. And as we go through glycolysis to produce the 2-pyruvate, it's going to be a yield of 2 ATP. With that, you're also going to have the 2 NADH, and from that you'll also get a yield of 5 ATP. From the glucose to 2-pyruvate, and then from 2-pyruvate to 2-acetyl-CoA, that pyruvate here is going to be oxidized and converted into CO2. With that, you'll get the additional 2 NADH, so that's going to be a total yield of 5 ATP as well. So from glucose to 2-acetyl-CoA, we've had a yield at this point of 10 ATP. 2 being from glycolysis, from glucose to 2-pyruvate, and then also we talked about the combined yields from the 2 NADH through that electron transport chain, which gives you the 5 ATP and the 5 ATP. So we've got glucose, which goes through glycolysis to 2-pyruvate. That 2-pyruvate is going to be oxidized into CO2, and then from that you'll get 2-acetyl-CoA. And from 2-acetyl-CoA, we're going to go into the citric acid cycle. And I was cramped for space here. But from the citric acid cycle, we're going to follow this large arrow over here to the right. And we're going to see more things going on with the electron transport chain. That's going to include the 6 NADH, right? And then the 2 FADH in and out of that electron transport chain. Those yields are going to be different from the NADH, which is going to produce 15 ATP, to the FADH, which is going to give you 3 ATP. So you can see that you've got your yield. So starting from back again, glucose to 2-pyruvate through glycolysis will yield that 2 ATP. Also through an electron transport chain, you're going to see the 2 NADH and the 2 NADH twice, from glucose to 2-pyruvate and 2-pyruvate to 2-acetyl-CoA. As mentioned, that's going to be your 10 ATP cumulatively. Right? Back to the citric acid cycle. Just kind of going back and forth and reviewing before I move forward with this ATP production. So from the citric acid cycle, we're going to come over here. This is going to be going on the electron transport chain, and that's going to give you that total yield of 18 ATP. So when you go over and you're looking through everything from glucose to 2-pyruvate to 2-acetyl-CoA to the citric acid cycle, also known as the Krebs cycle, and through the electron transport chain, you're going to have that release of 16 hydrogens. 12 will be for 6 NADH, which gives you the yield of 15 ATP, as discussed right here. And then you've got 4 for 2 FADH, which is going to yield that 3 ATP, which is going to be selected right here. Right, so these are going to be both reflective of the citric acid cycle and that electron transport chain. When you go down, you are also going to get 2 ATP formed by substrate phosphorylation. Let's see, I need to move this, there we go. That combination, that release of that 16 hydrogens through that electron transport chain from the Krebs cycle, plus the 2 ATP formed by substrate phosphorylation is going to yield the 20 ATP within that citric acid cycle. So if you combine everything that's essentially here going to be in the bold, let's see here, you're going to have 4 that are going to, you're going to have a total ATP yield from glycolysis, or a single glucose molecule, is going to be 32. 4 will be from substrate phosphorylation, and then also the 28 will be from oxidative phosphorylation. So when we talk about that, you've got your 5 and your 5 right here, so that's 10, plus 15, which is 25, and then plus the 3, which is 28. And so that's how you're going to get your yield of 28 oxidative phosphorylation. That's going to be part of your total ATP yield of 32. when we're using a single glucose molecule. All right. So then the next one, this is going to be, we're going to use palmitic acid. This is going to be ATP production from a single molecule of palmitic acid. I've gone ahead and I've got them in little separate squares. This is going to be on the left. You can see, let me see if I can move myself here so I'm not blocking anything. All right, maybe I can hide up in this top corner. Oh, maybe not. Here we go, right here in the middle. So we're going to start with our palmitic acid, and from that we are going to lose 2 ATP, right, as it goes in as it converts into that acetyl-CoA. So if we're going to start with palmitic acid, we will have a loss of 2 ATP into acetyl-CoA. As we're going from acetyl-CoA to transenol-CoA, the first phase of that beta oxidation, which is going to take place 7 times, you're going to have that dehydrogenation from FAD to FAD2. Okay, so we've got palmitic acid, we lose that 2 ATP in acetyl-CoA, and then you have transenol-CoA. Right, between acetyl-CoA and transenol-CoA, you're going to have that dehydrogenation. That's going to be the first step in beta oxidation. The second step in beta oxidation is going to be the hydration molecule that's going to be added from transenol-CoA to hydroxyacyl-CoA. So with that, that's the hydration. That's the second step in your beta oxidation. When we're going to hydroxyacyl-CoA to ketoacyl-CoA, you're going to have dehydrogenation a second time. That's your third step of beta oxidation. All right, then you have the NADH to NADH. With this, at the end, you're going to have myristyl-CoA and acetyl-CoA. From that, those are going to be your yields from that palmitic acid once you've gone through beta oxidation. This needs to go through by 7 times. So over here on the right, you can see the final cycle of beta oxidation. You have the 8 acetyl-CoAs, right? So that's going to yield 80 ATP, because if you look at this little legend down here, right, you've got 8 acetyl-CoAs, that yields 10 ATP from a single one. We have 8 of those, so that's going to give us 80 ATP. When we talk about the FADH, from that first phase of beta oxidation, from dehydrogenation, that's 7 FADH, which is going to yield about 10 point, the FADH yields about 1.5 ATP per FADH. We've got 7, so that's going to give us the 10.5 ATP. Second, we also have the 7 NADH. So when you see here in the third phase of beta oxidation, that's the NAD to NADH. That's going to be that 17.5 ATP yield that we're going to get from that. So when you look down here at the legend, the NADH is going to yield 2.5 ATP per NADH. In this instance, beta oxidation is going to go through 7 times, so we're going to multiply that times 7, right? That's going to give us our yield of 17.5 ATP. So if you add them up, 80 ATP from 8 acetyl-CoAs, right? You've got 10.5 ATPA from the FADH and 17.5 ATP from the NADH. When you combine that, that total yield is going to be 106. That's going to be from a single molecule of palmitic acid. All right? So that's going to be our ATP production from one single molecule of palmitic acid. Okay, let's see if I can move myself here. Next, we've got pathway interaction across exercise and intensity duration. The 2 pathways we have here are glycolysis. Now, there's going to be different steps based on if we're dealing with rapid or slow glycolysis. But for generalized, when we're talking about glucose and glycolysis, there's opportunities that it can be utilized for a high or low intensity exercise. Also, it allows for maximal effort through glycolysis, and the duration of exercise can be tailored for either short or long duration using glycolysis. So it is effective in that type of physical activity. For fat makes an excellent source for aerobic activity, particularly aerobic activity that is longer in duration, lower intensity. So if you have something where we've gone through and used our energy stores from such as muscle glycogen, if it's been depleted, we can then rely on fat as an excellent source to fuel that aerobic energy, particularly, like I mentioned, aerobic energy that is in maybe lengthier in duration but lower in intensity. With fat, there are some things with that. It does have a decreased rate of ATP production, so you're not going to use it for really rapid, fast, explosive movements like you may be able to rely on for glycolysis, for rapid glycolysis. But nonetheless, it is an effective energy store or energy system for those long, sustained bouts of exercise. Limiting factors of ATP production per pathway. Here, I'll move myself down here again. There we go. With glycolysis, when you talk about, there are some issues with enzyme inhibition. When you have excess ATP or NADH that's circulating, that's going to inhibit that enzyme activity. And with decreased enzyme activity, you're going to have an inhibition or a decreased rate of ATP production, which is something you can come across with glycolysis when you see that ATP and NADH. Additionally, with glycolysis, excessive oxygenation, or if you have an abundance of oxygenation, that can hinder glycolysis, which is going to, of course, the hindrance of glycolysis will lead to the inhibiting or decreased rate of ATP production. With respect to fat, that is going to be dependent on the breakdown of other substrates. Typically, we're thinking about carbohydrates. Usually when you run out of that glucose or that muscle or skeletal glucose, fat, that breakdown, it does rely on other substrates. It does need other energy sources to effectively break down substrates into ATP for energy. Also, when you have low levels of pyruvate, because that's going to be your second portion into that that pathway, that second step, low levels of pyruvate, which is a very critical portion of that ATP production per that pathway, low levels will negatively affect that citric acid cycle, because that's what you're going to need when you're going into that citric acid cycle. So low levels will affect that. So with fat, it is at risk for having some limiting factors with regards to certain lower levels of that pyruvate. And then as far as real-world application, I think it's really, really important with real-world application, like as the top bullet point mentions, that we're able to tailor nutritional needs to physical demands. However, we can't have exclusive reliance on that. Glycolysis certainly does play a role across many types of physical activities and across certainly almost nearly all sports. I would say all sports. But the energy substrate selection should be based on the goals or type of activities someone might want to do. It doesn't mean that if you select glycolysis or if you're using fat or glucose as a pathway or as a substrate for ATP production pathway, it doesn't mean that, oh, I'm going to use this type of substrate because this is going to give me this much energy. That's not always the truth. Some pathways may yield less energy, or may yield less ATP, but it doesn't mean that they're ineffective. So I think it's really important, like I said, you need to tailor those nutritional needs to the physical demands or the activity selected. So you're customizing that dietary intake. So just because something yields more ATP does not mean it might be the most appropriate substrate to rely on for certain physical activity or certain physical demands that are going to be placed on someone. And again, appreciation for these pathways can help athletes meet those physical demands. So understanding, as mentioned, the pathway which yields the most ATP might not be the most effective, might not be what we would want to rely on for a certain type of physical activity or demand. So when you have using fat as a substrate for energy or ATP conversion to ATP, if you have a physical activity that's going to require, short duration, rapid ballistic movement, just because the fat may yield more ATP doesn't mean that's the most effective. So tailoring, like I said, tailoring the nutritional needs, the type of activity is really, really important, rather than maybe picking whichever seems that it's going to have the most quote-unquote nutritional density or it's going to yield the highest ATP. So there's a lot of customization, and athletes that can appreciate this, I think they can capitalize on these types of biochemical pathways, if you will. So that's going to conclude my Cap 1. Thanks so much.